In this video, we'll be going over the bottom-up 3D approach of stone game. Let's go over the thought process. So let's convert the top-down memorization approach to a bottom-up approach. Now, where do we start? In the memorization approach, we have cached I, the current left boundary, the current right boundary, and the current player with score. This means we can create a 3D matrix score to keep track of the score for all combinations of I, J, and P. Now let's go over the pseudocode. So we're going to create a 3D matrix score. The x-axis represents I, the y-axis represents J, and the z-axis represents P. Now we're going to create a variable n, which is equal to pos.length, which is just the length of the input array. Now we're going to iterate through the left boundaries, iterate through from n-1 to 0, denoted as I. Then we're going to iterate through the right boundaries, 0 to n-1, denoted as J. Then we're going to iterate through the players from 1 to 0, denoted as P. Now, if I is greater than J, this means there are no more stones left. If there are no more stones left, the default score will be equal to 0. So we can just continue to the next iteration. This is because the input matrix, or the current matrix, the score matrix, has default values of 0 in it. Now, if I is equal to J, there's only one pile left. Now, if P is equal to 0, it's currently Alex's turn. And Alex only contributes positive values to the score, so I'm going to set score I, J, and P to positive piles I. Else is currently Lee's turn, and Lee always contribute negative values to the score, so I want to set score piles to negative piles I. Then we can continue to the next iteration. Now, if P is equal to 0, it's currently Alex's turn. Alex has two choices, picking the stone pile from the left side or picking the stone pile from the right side, and he wants to maximize the score. So I want to set score IGP to the larger value between picking from the left side. If he picks from the left side, I increase by 1, and then the player's turns to 1, because in the next turn, it's going to be Lee's turn, and we will increment by the current number of stones that I've gotten, and also the number of stones if he picks from the right side. If he picks from the right side, J decrements by 1, player changes, and also increment by the number of stones on the right side. Else is currently Lee's turn. Lee wants to minimize the score, and any stones that Lee gets will decrement the score. So I want to set the score to the smaller value between picking from the left side. So if he picks from the left side, I increments by 1, J stays the same, our player go back to 0, because in the next turn, it's going to be Alex's turn, and then he will decrement by the number of stones, decrement the score by the number of stones that he's gotten. Also, similar case here. If he picks from the right side, J decrements by 1, and then the player goes back to 0 to Alex's turn, and then he would decrement by the amount of stones that he's gotten. Then we can return score 0, n-1, and 0. Oh, we'll return true if the score is greater than 0, which means Alex has won. So this just means it's the score with the current left and right boundaries, and Alex starting first. Because it's the left boundary, it's the right boundary, and 0 just means Alex. This is Alex's turn. Alex starting first. Now let's go over to time and space complexity. For the time complexity, we get O of n squared times 2, so just O of n squared, where n is the length of the input array. This is just our nested for loops. And our space complexity, similar case. This is our square matrix or score matrix. Now let's go over the code. We're going to create a variable n to keep track of the length of the input array. Then we're going to create a 3D matrix score to keep track of the score for all combinations of IJP. Then we're going to iterate through the left boundaries. We're going to iterate through the right boundaries. We're going to iterate through the players. Now, if I is greater than j, this means there are no more stone piles left, and also the default score will be equal to 0. So we can just continue to the next iteration because the matrix score already has default values of 0. Now, if I is equal to j, then if it's currently, so the score will be, so if the current player is equal to 0, which means Alex's turn, then it's going to be positive values. Else, if Lee's turn, it's going to be negative values. Then we can continue to the next iteration. Now, if P is equal to 0, it's currently Alex's turn. Alex wants to maximize the score, and then he will have two choices, picking from the left side or picking from the right side, and he will pick the larger value between the two. So if he picks from the left side, I increase by 1. The players change to 1. It's going to be Lee's turn, and increment by the amount of piles they've gotten. And then also, if he picks from the right side, j will decrement by 1. The players turn to 1, and then increment by the amount of stone that he have gotten from the right side. Else, it's currently Alex's turn. No, it's currently Lee's turn. If it's Lee's turn, he wants to minimize the score. And all of the stones that Lee get will decrement the score. So he wants to take the smaller value. If he takes from the left side, I increase by 1. The players change back to 0. In the next turn, it's going to be Alex's turn again. Then we get decrement by the amount of stones they've gotten. And also, if he picks from the right side, then the player goes back to Alex. J gets decremented by 1. And then he will decrement by the amount of piles. Now we can return the score with the left boundary starting at 0, right boundary starting at n-1, and the initial player is equal to 0. So if the score is greater than 0, this means Alex has won. Let me know if any questions in the comment section below.